On the night of October 19, 2017, the Pan-STARRS 1 telescope perched atop Haleakala volcano in Maui captured something that should not exist. The astronomers reviewing the data felt their certainty crumble as the numbers refused to make sense. The object designated as /2017 U1 was moving through our solar system at nearly 90,000 kilometers per hour. But that wasn't what made veteran scientists reach for their phones at 3 in the morning. It was the trajectory. The thing was traveling wrong. Every comet, every asteroid, every piece of cosmic debris we have ever tracked follows the fundamental architecture of our solar system, orbiting roughly along the same flat plane where the planets circle our sun. This object had plunged downward from above that plane at a steep angle, as if it had taken deliberate aim at our solar system from somewhere in the vast darkness between stars. It was already leaving when we found it, already racing back toward interstellar space, and the gravity calculations showed something that made no physical sense. It was accelerating, not slowing down as it should have been after whipping around our sun, but speeding up, as if something were pushing it forward into the void. The shape revealed by subsequent observations violated everything we know about natural cosmic objects. Analysis showed an aspect ratio of approximately 10:1. A cigar, a needle, a shape so elongated that no known natural process could sculpt it. Every asteroid humanity has studied is roughly spherical or potato-shaped, worn smooth by billions of years of collisions and gravitational forces. Every comet is an irregular chunk of ice and rock. Nothing in nature creates a 10:1 ratio. Nothing except intelligence. Nothing except design. Within weeks, the object had been named Oumuamua, a Hawaiian word meaning scout or messenger arriving from the distant past. The name would prove more prophetic than anyone intended. Scientists scrambled to gather data before it disappeared forever beyond our reach, accelerating into interstellar darkness at speeds our fastest spacecraft could never match. But crucial opportunities had already been lost. The object had been in our solar system for weeks before detection, possibly months, passing its closest approach to Earth while we remained completely unaware. By the time we knew it existed, our window to study it was already closing. Then came the anomaly that would fracture the scientific community. Professor Abraham Loeb, chair of the astronomy department at Harvard University, examined the acceleration data and reached a conclusion that would make him either a visionary or an outcast. The mathematics suggested the object was being pushed by solar radiation pressure, which meant it had to be extremely thin and light, like a sail catching the sun's photons. But no natural object could maintain such a structure across interstellar distances. Loeb proposed what others thought but dared not speak aloud. Perhaps Oumuamua was artificial. Perhaps it was a light sail, a piece of technology from another civilization, tumbling through our cosmic neighborhood like a derelict ship passing in the night. The scientific establishment recoiled. Alternative explanations emerged, each more strained than the last. Perhaps it was a nitrogen iceberg. Perhaps it was a hydrogen cloud somehow holding together. Perhaps it was outgassing in a way that left no visible trail and violated our understanding of cometary behavior. The proposed natural explanations became increasingly exotic, requiring special conditions and unprecedented physics, while the artificial hypothesis required only what we already know is possible, because we ourselves have designed light sails and considered them for interstellar travel. The data we needed to settle the question will never exist. The critical measurements were never taken. The high-resolution images were never captured. We had one chance to photograph it, to analyze its surface, to scan for radio emissions or heat signatures, and we missed it because we didn't know to look. Oumuamua is now beyond the orbit of Neptune, beyond our ability to chase or study, racing back toward the constellation Lyra at a speed that will carry it to interstellar space forever. We are left only with fragments, with incomplete data sets, with mathematical curves that end in questions rather than answers. The possibility hangs in the darkness like a held breath. What if it was them? What if the first definitive proof of alien technology passed through our solar system while we stared at our phones and worried about terrestrial concerns? What if contact came and went, and we realized it only in retrospect, watching the messenger disappear into the cosmic ocean with information we will never recover. The thought carries a particular species of dread, the horror of the missed encounter, the permanent loss of what might have been the most important moment in human history. And it raises darker questions still. If Oumuamua was artificial, was it functional or derelict? Was it observing us as it passed, collecting data about this curious species that has only just begun reaching beyond its own atmosphere? Or was it simply wreckage, the broken remnant of some unimaginable voyage, tumbling through space long after its creators turned to dust? If civilizations can die and their artifacts drift forever through the void, what does that suggest about the cosmic silence that surrounds us? The scientists who trained telescopes on Oumuamua's fading light saw something humanity had never witnessed before, an interstellar object, confirmed and undeniable, proving that things can travel between the stars. But they may have seen something more. They may have documented the moment when humanity was weighed and found wanting, when we proved ourselves not yet ready to recognize intelligence when it literally passes before our eyes. The data sits in archives now, incomplete and haunting, evidence of either the most important astronomical discovery of our time or simply an unusual rock. We will never know which. Oumuamua has made sure of that. The telescope on Haleakal continues its programmed sweeps of the night sky, searching for objects that might threaten Earth or reveal cosmic secrets. The astronomers have returned to their regular work, tracking ordinary asteroids and cataloging distant galaxies. But some still turn their instruments toward the point in space where Oumuamua vanished, knowing they are looking at emptiness, knowing the messenger is long gone, knowing that somewhere in the darkness between stars, it continues its inexplicable journey, carrying answers to questions we learned to ask too late. October 19th, 2017. The night shift at the Pan-STARRS telescope on Haleakal, Maui. Robert Warwick stared at his computer screen with growing unease, watching the same calculation fail for the third time in a row. The asteroid he had flagged hours earlier kept producing impossible results. The trajectory software insisted the object was moving wrong, too fast, at the wrong angle. His first thought was mundane, even tedious. Another bug in the system. Another late-night debugging code instead of hunting for space rocks. He ran the numbers again. Same result. The object designated a /2017 U1 had been captured in the telescope's wide field of view as it swept the night sky, searching for near-Earth asteroids that might pose a threat to our planet. This was routine work, the kind of observation that happened hundreds of times each year. Except this time, the math refused to cooperate. Every orbital calculation suggested something that couldn't possibly be true. The object wasn't bound to our solar system. It wasn't orbiting anything at all. Warwick felt the first stirrings of something between excitement and dread. He checked his work methodically, looking for the error he assumed must be there. He verified the telescope's tracking data. He cross-referenced the object's position against star catalogs. He recalibrated the software parameters. Nothing changed. The numbers kept telling him the same impossible story. This thing had come from somewhere else. Not from the Kuiper Belt. Not from the Oort cloud. From somewhere beyond our sun's gravitational embrace entirely. The implications began to cascade through his mind like falling dominoes. If the trajectory calculations were correct, this object had been traveling through the vast emptiness between stars for an incomprehensible span of time. Millions of years, tens of millions perhaps, drifting through the cosmic void while our ancestors were still learning to walk upright, while dinosaurs ruled the Earth, while life itself was perhaps still finding its foothold on our young planet. And now, by pure chance, it had wandered into our neighborhood, falling toward our sun in a hyperbolic arc that would slingshot it back out into the darkness forever. He reached for his phone. This required confirmation. This required more eyes, more telescopes, more data. Because if he was right, if the software wasn't lying to him, then humanity was about to observe something that had never been documented in the entire history of astronomy. The first confirmed interstellar visitor. The first object proven to have come from beyond our solar system's boundaries. Within hours, telescopes around the world began swiveling toward the coordinates. The race had begun, Though nobody quite realized it yet, the object was already leaving. Already accelerating away from the sun, climbing back up out of the gravity, well, it had briefly fallen into. Every hour that passed meant dimmer observations, weaker signals, fewer photons reaching our instruments. The window of opportunity was closing with brutal, inexorable speed. They named it Oumuamua, a Hawaiian word meaning scout, or messenger arriving from the distant past. The name felt appropriate, almost prophetic. This was indeed a messenger, carrying information about the interstellar medium, about the space between stars that remained largely mysterious to us. But it was a messenger that wouldn't wait around to be properly interrogated. The observations began in earnest, and with each new data point, the strangeness multiplied. Astronomers watched in growing bewilderment as the object's brightness fluctuated wildly, changing by a factor of 10 every 7.3 hours. This suggested a rotation, a tumbling end-over-end motion through space. But the magnitude of the variation was extraordinary. Most asteroids brightened and dimmed by perhaps 20 or 30% as they rotated. Oumuamua's fluctuations were extreme, violent, suggesting a shape unlike anything in our cosmic neighborhood. The best models indicated something elongated, stretched, like a cosmic cigar or perhaps a thick pancake. The aspect ratio suggested it was at least 10 times longer than it was wide. Some calculations pushed that ratio even higher. This wasn't just unusual. This was potentially unprecedented. Nothing in our solar system looked quite like this. No asteroid, no comet, no captured fragment of planetary formation exhibited such an extreme geometry. Day 3 of observations brought another puzzle. As Oumuamua had approached the sun, crossing inside Earth's orbit, astronomers had expected to see the telltale signs of cometary activity. When ice-laden comets venture close to our star's warmth, they begin to outgas, releasing water vapor and other volatiles that form the characteristic tail stretching millions of miles behind. But Oumuamua remained stubbornly inert. No tail appeared. No coma of gas and dust surrounded it. Spectroscopic analysis detected no trace of the expected outgassing. It looked, for all intents and purposes, like an asteroid. Rocky died, dry, dead. Not. But asteroids don't come from interstellar space. The dynamics were all wrong. Asteroids formed in solar systems, trapped in orbital resonances around their parent stars. The idea of a rocky body being ejected with enough velocity to escape stellar gravity and wander the galaxy was theoretically possible, but vanishingly rare. And even if such an ejection occurred, the object should have shown some signs of its violent departure. Impact scars. Fragmentation. Something. The spectral analysis added another layer to the mystery. Oumuamua's surface appeared reddish, a deep rusty color that suggested long exposure to cosmic radiation. Interstellar space is not empty. It's crisscrossed by high-energy particles, cosmic rays that sleeted through the void at relativistic speeds. Over millions of years, these particles would bombard any object's surface, altering its chemistry, creating complex organic molecules called tholins that gave the surface that characteristic reddish hue. The color itself was evidence supporting the interstellar origin hypothesis. This thing had been traveling through deep space for an enormously long time. By day 7, the urgency in the astronomical community had reached fever pitch. Oumuamua was accelerating away faster than expected. Not dramatically faster, but measurably so. The deviation was small, less than 1%, but it was real, and it was consistent. Something was pushing it, providing a tiny but persistent force that couldn't be explained by gravity and solar radiation pressure alone. The effect was similar to what you'd expect from cometary outgassing, but there was no visible outgassing. No tail, no coma, no detectable emissions of any kind. Theories multiplied wildly. Perhaps the outgassing was happening in a way we couldn't detect, releasing molecules that were transparent to our instruments. Perhaps the object's strange shape was causing unusual radiation pressure effects. Perhaps there was some other force at play, something we hadn't accounted for in our models of orbital mechanics. Each explanation raised new questions, opened new avenues of uncertainty. The telescopes kept tracking, kept gathering every photon they could capture from the rapidly receding visitor. Teams of astronomers worked around the clock, coordinating observations across hemispheres, passing the target from one facility to another as Earth rotated. The data accumulated in fits and starts. Clouds interfered. Technical problems delayed observations. The object grew dimmer with each passing day, harder to spot against the background stars. Day 9. Oumuamua was now fainter than most telescopes could reliably track. Only the largest instruments in the world could still capture usable data. The Hubble Space Telescope was pressed into service, its precious observation time redirected to squeeze out a few more data points from the departing enigma. Every image was analyzed immediately, feeding into models that grew more complex and more uncertain in equal measure. The scientific papers began appearing at a frantic pace, published in preprint form before peer review, because everyone understood the urgency. This was a once-in-a-lifetime event, possibly a once-in-human history event, and the window was slamming shut. Researchers proposed wildly different interpretations of the same data. Some insisted it must be a comet, just one with an unusual composition that prevented visible outgassing. Others argued for a fragment of a disintegrated planet, ejected when its parent star went supernova billions of years ago. A few suggested more exotic possibilities. A chunk of solid hydrogen, a cosmic dust bunny held together by organic compounds. Each theory had problems, holes that couldn't quite be filled by the available evidence. Day 11. The last useful observations were captured. Oumuamua had dimmed beyond the threshold where even our most powerful telescopes could extract meaningful data. It was still out there, still tumbling through space, still accelerating on its mysterious trajectory toward the constellation Pegasus. But as far as human observation was concerned, it had vanished, returned to the darkness from which it had briefly emerged. The astronomers were left with their data sets, their conflicting models, their unanswered questions. 11 days. That's all humanity had been given to study the first confirmed visitor from another star system. 11 days to observe, to measure, to attempt to understand something that had traveled through space longer than our species had existed. And at the end of those 11 days, Oumuamua had slipped away, carrying its secrets back into the interstellar void, leaving behind only a cascade of mysteries, and the haunting certainty that we had missed something, that with more time, with better instruments, with a few more observations, we might have solved the puzzle. But time had run out, and the visitor was gone, accelerating toward the edge of our solar system and the infinite beyond, never to return. The numbers started appearing about 3 weeks after Oumuamua had already vanished from our telescopes, streaking back into the darkness between stars. Scientists were hunched over their computers, running final analyses on the trajectory data, when something impossible emerged from the calculations. The object had accelerated. Not much, just a tiny deviation from what Newton's laws predicted, but in the precision world of celestial mechanics, tiny deviations are everything. They're the difference between understanding and mystery, between the known universe and something else entirely. Marco Micheli was the astronomer who first caught it. He was working at the European Space Agency's Operations Center, double-checking the positional measurements against predicted values. The kind of routine work that usually confirms what you already know. Except this time, the numbers didn't match. Oumuamua was moving faster than it should have been, and more disturbing, it wasn't moving in quite the direction gravity alone would take it. He ran the calculations again. Then again. The deviation persisted, stubborn and real, staring back at him from the screen like an accusation. The acceleration was small, about 1/10,000th of Earth's gravity, but it was there, unmistakable in the data. And it had a specific character to it, a signature that scientists recognized immediately. This was non-gravitational acceleration, the kind of push that requires something other than gravity to explain it. In our solar system, there's really only one natural phenomenon that causes this kind of behavior: outgassing from comets. When comets approach the sun, their icy surfaces heat up and sublimate, turning directly from solid to gas without passing through a liquid phase. This gas jets outward from the surface, carrying dust with it, creating those magnificent glowing tails that have frightened and fascinated humanity for millennia. But those jets also act like tiny rocket engines, pushing the comet in directions that gravity alone cannot explain. The effect is well understood, predictable, measurable. Astronomers had been accounting for cometary outgassing in their calculations for decades, so the initial reaction to Oumuamua's acceleration was almost relief. Of course, it must be a comet after all. The mystery solved itself. The unusual tumbling motion, the strange elongated shape, the reddish color, all of it could be reconciled if we just accepted that Oumuamua was outgassing like any normal comet, pushing itself along as frozen volatiles erupted from its surface. Except for one small problem that became a very large problem the moment anyone looked closely at the observation data. There was no gas. None. Zero. Far. Not a single telescope, and dozens had watched Oumuamua intensely during its passage, had detected even a whisper of outgassing. No coma, the fuzzy cloud of gas and dust that surrounds active comets. No tail. No spectroscopic signature of water vapor, carbon dioxide, carbon monoxide, or any of the other materials that comets typically release. The Spitzer Space Telescope, specifically designed to detect the infrared signature of dust, saw nothing. Radio telescopes searching for the telltale signs of molecular emission found only silence. Oumuamua had accelerated exactly like a comet, while showing absolutely none of the evidence that it was actually doing so. It was as if someone had invented an invisible rocket fuel, one that could push an object through space while leaving no trace, no exhaust, no signature whatsoever. The scientific community found itself impaled on the horns of an impossible dilemma. Every observation said asteroid, a dead rock tumbling through space. But the trajectory said comet, an active body releasing material. You couldn't have both. It violated the basic categories that astronomers had used to classify objects for centuries. Things were either active or inert, outgassing or stable, comets or asteroids. Oumuamua refused to fit into either box. The unease began slowly, a creeping sensation in laboratories and universities around the world. Scientists started proposing explanations, each one more exotic than the last, each one requiring a set of circumstances so specific and unlikely that accepting it felt like grasping at straws in a windstorm. Maybe, some suggested, Oumuamua was outgassing pure hydrogen ice. Hydrogen molecules are so light, so hard to detect, that perhaps they had simply missed it. The object could have been a hydrogen iceberg, frozen in the deep cold between stars, now sublimating as our sun warmed it. The hypothesis had a certain elegance, but it immediately ran into problems. Hydrogen ice is extraordinarily fragile, barely able to hold together even in the frozen depths of interstellar space. For Oumuamua to be made of hydrogen ice and still maintain its structural integrity after a close pass by the sun, after accelerating and tumbling through space, required conditions so precise they bordered on the fantastical. You'd need exactly the right temperature history, exactly the right formation environment, exactly the right protective coating. The scenario was possible in the way that winning the lottery 5 times in a row is possible, technically within the laws of probability, but so unlikely that believing it feels absurd. Then came the nitrogen iceberg hypothesis. Perhaps Oumuamua was a chunk broken off from a Pluto-like world in another star system, composed primarily of nitrogen ice, like the frozen plains of Pluto's Sputnik Planitia. Nitrogen can sublimate, providing thrust, and might be harder to detect than water vapor. Again, the idea had a certain appeal, but again, the specific requirements strained credibility. You needed not just a Pluto-like exoplanet, but one that had been violently disrupted, sending chunks of its surface into interstellar space. You needed that chunk to survive the journey without completely sublimating away, despite traveling for millions or billions of years through the galaxy. You needed it to arrive at our solar system with exactly the right shape, the right spin, the right properties to explain all of Oumuamua's strange behaviors. Each explanation required stacking unlikely circumstance upon unlikely circumstance, building towers of coincidence that threatened to topple under their own implausibility. Scientists found themselves arguing about scenarios they would have laughed off a year earlier, grasping for any natural explanation no matter how contrived. But the most disturbing aspect of the acceleration wasn't just that it existed. It was the specific nature of it, the vector and timing that emerged from detailed analysis. The acceleration was radial, pointing directly away from the sun, exactly as you'd expect from outgassing driven by solar heating. This wasn't random. This wasn't chaotic. This was oriented, purposeful in its geometry, if not necessarily in its intent. Moreover, the magnitude of the acceleration seemed to remain relatively constant despite Oumuamua's wild tumbling motion. The object was rotating, flipping end over end every 7 to 8 hours, yet somehow, the acceleration maintained its sun-pointing direction. For natural outgassing, you'd expect the thrust to vary as different parts of the surface rotated into sunlight, creating an uneven fluctuating push. But Oumuamua's acceleration was smooth, steady, almost controlled. That word, controlled, began appearing in scientific papers with increasing frequency, always carefully hedged with qualifications and alternative explanations. But there nonetheless. The data suggested something that was either controlling the acceleration or being controlled by it. The behavior was too consistent, too oriented, too perfect to easily reconcile with a chaotically tumbling object, randomly venting gas from its surface. Some researchers began examining whether the tumbling motion itself might be designed to average out the thrust, whether the specific rotation rate and axis might be chosen to produce exactly this kind of steady, radial acceleration. But that line of thinking led to uncomfortable places, to questions about intention and purpose that science is not well equipped to handle. Karen Meach, the astronomer who had led many of the initial observation campaigns, spoke carefully about the growing mystery in interviews and papers. She emphasized the need for natural explanations, the importance of not jumping to extraordinary conclusions without exhausting every ordinary possibility. But even she couldn't fully hide the puzzlement in her voice when discussing the acceleration. The numbers didn't add up. The observations didn't cohere. Something was wrong with the picture, like an equation that balances everywhere, except one crucial term. Other scientists were less restrained. They pointed out that the simplest explanation for an object that accelerates without visible propellant is that the propellant isn't visible to us, either because it's something we don't know how to detect, or because the propulsion method doesn't require expelled mass at all. Solar sails came up repeatedly in these discussions, thin reflective surfaces pushed by sunlight itself, requiring no fuel, leaving no exhaust. The acceleration profile matched what you'd expect from a tumbling solar sail remarkably well. But accepting that explanation meant accepting that Oumuamua was artificial, a piece of technology rather than a natural object. And that conclusion carried implications that made even the most open-minded scientists hesitate. If it was artificial, who made it? Why was it here? Was it still functioning, or just drifting debris from a civilization long dead? The questions multiplied faster than answers could possibly arrive. The scientific crisis deepened as more data was analyzed and published. Papers appeared proposing increasingly baroque natural mechanisms, each one meticulously researched and mathematically rigorous, each one requiring just a few more unlikely coincidences to work. The community was fracturing into camps, not along lines of belief versus skepticism, but along lines of which impossible thing you were willing to accept. Impossible physics or impossible engineering. An object that violated our understanding of how natural bodies behave, or an object that suggested we were not alone in the universe. Meanwhile, Oumuamua itself continued its journey outward, already far beyond the reach of even our most powerful telescopes, carrying its secrets back into the darkness from which it came. The window of opportunity had closed. We had one chance to study the first known interstellar visitor, and it had left us with more questions than answers, with data that refused to resolve into a coherent picture no matter how many times scientists rearranged the pieces. The acceleration remained, unexplained and unexplainable by any comfortable theory, a numerical ghost haunting the trajectory calculations. Something had pushed Oumuamua. Something had given it that extra velocity, that non-gravitational boost through our solar system. Every attempt to identify that something through natural processes required scenarios so contrived they felt more like storytelling than science. And so the mystery persisted, deepened, became not just a puzzle about one strange object, but a crisis of understanding about what was possible and what was real. The numbers on the screen didn't lie, but they told a story that no one quite knew how to read. The object tumbled through the inner solar system at over 54 miles per second, and Professor Avi Loeb couldn't stop thinking about what it wasn't doing. It was October of 2017 when the Pan-STARRS telescope in Hawaii first caught sight of the interstellar visitor, and by the time astronomers around the world turned their instruments toward it, Oumuamua was already leaving, already fading into the cosmic dark from which it had emerged. But in those precious few weeks of observation, the object revealed characteristics that defied every conventional explanation. And Loeb, the chair of Harvard's astronomy department, a man who had spent decades building one of the most respected careers in astrophysics, was about to stake that entire reputation on a single shattering question. What if it was artificial? The academic storm that would follow his 2018 paper wouldn't just challenge Loeb's standing in the scientific community. It would expose something far more unsettling about the nature of modern science itself, about the invisible boundaries that separate acceptable inquiry from professional suicide, about what happens when a scientist dares to follow evidence toward a conclusion that the establishment finds intolerable. Loeb's office at Harvard overlooked a campus where some of humanity's greatest minds had wrestled with the fundamental questions of existence. Now he sat at his desk, reviewing data that seemed to point toward an answer so profound that his colleagues would rather dismiss it entirely than consider its implications. The numbers were there, stark and undeniable. Oumuamua had accelerated as it swung around the sun, a subtle push that couldn't be explained by gravity alone. When comets accelerate like this, they do so because the sun's heat vaporizes their icy surfaces, creating jets of gas that act like tiny rocket engines. This outgassing always leaves a visible trail, a characteristic coma of gas and dust that astronomers can detect from millions of miles away. Oumuamua showed none of this. No coma, no tail, no outgassing whatsoever. Yet it accelerated anyway, deviating from the trajectory that gravity alone would have prescribed. Loeb found himself returning to the same inescapable logic. If not a rocket effect from outgassing, then what? The answer that kept emerging from his calculations was both elegant and terrifying in its implications. Solar radiation pressure, the gentle push of sunlight itself, could account for the acceleration, but only if the object had a very specific geometry. It would need to be extremely thin relative to its surface area, less than a millimeter thick, in fact. A pancake tumbling through space, a sail catching the solar wind. The shape data supported this hypothesis in ways that made Loeb's pulse quicken. Observations showed that Oumuamua's brightness varied by a factor of 10 as it rotated, suggesting an extremely elongated or flat geometry. The estimates ranged, but the most extreme models proposed a length-to-width ratio of 10 to 1 or even greater. No known natural process creates objects with such proportions. Asteroids and comets are typically rough spheres or irregular chunks, shaped by gravity and collisions into relatively compact form. But a 10 to 1 ratio? That was the geometry of something designed. That was the shape of theoretical light sails that physicists had been proposing for decades as a means of interstellar travel. The concept wasn't science fiction. Engineers at NASA and other space agencies had seriously studied light sail technology. The idea was beautifully simple. Build an ultra-thin reflective surface, large in area but minimal in mass, and let the continuous pressure of sunlight accelerate your spacecraft over time. No fuel needed. No engines. Just the patient, persistent push of photons against a reflective surface. For interstellar distances, where conventional rockets become absurdly impractical, light sails offered one of the few theoretically viable solutions. And here, tumbling through our solar system, was an object whose characteristics matched those theoretical designs with uncanny precision. Loeb knew what he was about to do. He understood the professional consequences of putting his name on a paper that suggested, even as one possibility among many, that Oumuamua might be of artificial origin. His co-author, Shmuel Bialy, a postdoctoral fellow, had worked through the mathematics with him, and the numbers held. The paper was careful, measured, academic in its language. They didn't claim proof. They proposed a hypothesis that fit the observed data. In the careful language of scientific papers, they suggested that an artificial origin should be considered among the possible explanations. The paper appeared in the Astrophysical Journal Letters in November of 2018, and the response was immediate and vicious. Loeb had expected skepticism. Science thrives on rigorous debate, on the challenging of new ideas through evidence and argument. What he encountered instead was something that looked less like scientific discourse and more like an autoimmune response, as if the body of mainstream astronomy were attacking a foreign presence that threatened its fundamental integrity. Colleagues who had worked with him for years suddenly distanced themselves. Interviews with other astronomers produced quotes dripping with condescension and barely concealed anger. The hypothesis was called irresponsible, attention-seeking, damaging to the credibility of serious astronomy. What struck Loeb most forcefully was not that his colleagues disagreed with him. It was the emotional intensity of their disagreement, the sense that he had violated some unspoken rule that transcended the normal bounds of scientific debate. They didn't just think he was wrong. They seemed personally offended that he had asked the question at all. The vitriol came from respected voices in the field, people whose work Loeb admired, and their objections often bypassed his actual arguments to attack the very premise of considering an artificial explanation. The alternative theories proposed to explain Oumuamua's characteristics grew increasingly exotic. Some suggested it was a nitrogen iceberg, despite nitrogen ice being extraordinarily rare in interstellar space. Others proposed that it was a fractal dust aggregate, a fluffy collection of particles never before observed. These explanations required their own leaps of assumption, their own departures from conventional asteroid models. Yet they were treated as inherently more acceptable than Loeb's light sail hypothesis for one simple reason. They didn't invoke intelligence. They didn't raise the specter of alien technology. Loeb began to perceive a deeper pattern in the scientific establishment's resistance. The possibility of extraterrestrial intelligence occupied a peculiar place in modern astronomy, simultaneously acknowledged as likely and treated as professionally toxic. The same scientists who agreed that billions of potentially habitable planets existed in our galaxy alone, who accepted that life probably arose elsewhere in the universe, reacted with hostility to any suggestion that we might have actually detected evidence of that life. The theoretical possibility of aliens was acceptable, even fashionable. The practical investigation of potential alien artifacts was career poison. He gave lectures where he articulated his reasoning with the same clarity that had made him one of the most effective science communicators in astronomy. The logic was straightforward. Oumuamua came from interstellar space, our first confirmed interstellar object. Its characteristics didn't match known natural objects. Its shape and acceleration profile did match theoretical designs for artificial light sails. The scientific method, as Loeb understood it, required considering all hypotheses consistent with the data, including unconventional ones. Extraordinary claims required extraordinary evidence, yes, but extraordinary dismissal of evidence required justification too. The media attention intensified the backlash. Loeb appeared on news programs, wrote op-eds, explained his reasoning to audiences beyond the academic world. To his critics, this public engagement was itself evidence of his injuriousness, as if real scientists were supposed to confine even their most significant ideas to the narrow readership of specialized journals. The fact that people were fascinated by the possibility of an alien artifact became, in the eyes of his detractors, a reason to be more skeptical rather than more rigorous in examining the evidence. But there was another dimension to Loeb's hypothesis, one that he discussed less frequently in public forums, but that haunted his private considerations. If Oumuamua was indeed a light sail, if humanity's first confirmed detection of alien technology had just slipped past us and back into the void, what did its condition tell us? The object was tumbling, rotating chaotically rather than in the stable configuration you'd expect from an operational spacecraft. It didn't emit any signals that our radio telescopes could detect. It didn't alter its course or show any signs of active control. If it was artificial, it appeared to be dead, a derelict, a piece of cosmic debris from a civilization that had built it perhaps millions of years ago, and then, perhaps, ceased to exist. This possibility carried implications more chilling than the mere existence of aliens. It suggested that the galaxy might be littered with the remains of dead civilizations, that intelligence might arise only to extinguish itself, that the great silence we hear when we listen for alien signals might not be because intelligent life is rare, but because it doesn't last. Oumuamua, in this interpretation, became a ghost ship sailing through the solar system, a memorial to beings who had mastered interstellar travel, only to vanish into the same cosmic indifference that awaits all things. Loeb wrestled with the mathematical implications of this scenario. If light sails were common detritus from technological civilizations, how many might be drifting through space at any given time? How often might they pass through our solar system undetected? Oumuamua was discovered only because it passed relatively close to Earth, and because we happened to have a telescope pointed in the right direction at the right time. How many others had we missed? How many artifacts might be floating through the dark spaces between stars, slowly eroding under cosmic radiation, their purposes forgotten, their makers long extinct? The hostility Loeb faced from the scientific establishment seemed, in his analysis, to stem from something deeper than mere skepticism about a single hypothesis. It revealed an institutional resistance to truly grappling with the implications of contact, even contact with the remains of a dead civilization. The possibility that we might be alone in the universe was terrifying, yes. But the possibility that we might not be alone, that intelligence might arise and flourish, and then inevitably fade, that our own trajectory might lead toward the same silent extinction. Perhaps that was more terrifying still. As months passed, and Oumuamua receded beyond the reach of even our most powerful telescopes, Loeb continued to refine his arguments and defend his hypothesis. He wrote a book, arguing not just for the light sail interpretation, specifically, but for a broader openness to evidence-based investigation of potential alien artifacts. He challenged his colleagues to explain why hypotheses invoking novel natural phenomena were acceptable, while hypotheses invoking known technology, merely applied by non-human intelligence, were beyond the pale. The debate never truly resolved. Oumuamua faded into the darkness, carrying its secrets with it. No consensus emerged in the scientific community. But something had shifted. Loeb had demonstrated that it was possible to ask the forbidden question and survive professionally, if barely. He had shown that the evidence, however ambiguous, was substantial enough to warrant serious consideration of artificial origin. And he had exposed the deep discomfort that pervades modern science when confronted with phenomena that might, just might, indicate we are not the only intelligence to have gazed up at the stars and wondered what lies beyond. The object continues its journey now, tumbling through the interstellar void, indifferent to our debates about its nature. Whether natural or artificial, whether an odd-shaped asteroid or the broken remnant of alien engineering, it has already passed beyond our ability to study it further. We had our chance, those few weeks in late 2017, and we learned just enough to ask questions we may never be able to answer. The first interstellar visitor became a mirror reflecting our own assumptions and fears, our curiosity, and our reluctance to follow that curiosity to its most profound conclusions. And somewhere in the data, in the tumbling rotation and the unexplained acceleration, lies either the mundane truth of an unusual rock or the extraordinary truth that we are not alone, and perhaps never were. On the 19th of October, 2017, a graduate student named Robert Warwick was reviewing data from the Pan-STARRS telescope in Hawaii when he noticed something that would change our understanding of the cosmos forever. A streak of light, moving at impossible speeds, traced across his screen. The object was designated 1I/2017 U1, but the world would come to know it by its Hawaiian name, Oumuamua, meaning scout or messenger arriving from the distant past. But by the time humanity realized what had entered our solar system, it was already racing away from us, and we were utterly powerless to catch it. For decades, scientists had dreamed of this moment, the detection of an interstellar visitor, an artifact from another star system, carrying secrets about the formation of alien worlds, the chemistry of distant nebulae, perhaps even evidence of life beyond Earth. We had spent billions on SETI programs, scanning the heavens for radio signals, building ever more sensitive instruments to detect the faintest whisper from another civilization. We had imagined first contact in 1,000 different ways. Yet, when that moment finally arrived, when an object from beyond our solar system came within reach for the first time in human history, we were caught completely unprepared. No space agency on Earth had protocols in place for intercepting interstellar objects. No mission designs sat waiting on shelves, ready to be activated. No spacecraft stood fueled and ready to launch at a moment's notice. We had built elaborate castles in the sky, entire frameworks for how we might communicate with alien intelligence, but we had forgotten the most basic preparation: what to do if something actually arrived. The timeline of our failure reads like a tragedy in slow motion. Oumuamua had actually entered our solar system on September 9, 2017, more than a month before its discovery. It had passed within just 15 million miles of Earth on October 14th, closer than many comets that we track with ease. But we missed it. Our telescopes were pointed elsewhere, our attention divided among 1,000 other priorities. When Reich finally spotted it 5 days later, the object was already accelerating away from us, pulled by the sun's gravity into a slingshot trajectory that would fling it back into interstellar space at over 58,000 miles per hour. With every passing hour, Oumuamua grew more distant, more unreachable, slipping through our fingers like water. The initial days were consumed by confusion and verification. Was this object real? Was it truly interstellar? Scientists double-checked their calculations, verified the orbital parameters, traced the trajectory backward through space. They discovered that Oumuamua had come from the direction of the star Vega, traveling through the void for hundreds of millions of years before its chance encounter with our sun. Its orbit was hyperbolic, not elliptical, meaning it was not bound by our sun's gravity. It had come from somewhere else, and it was going somewhere else, and Earth just happened to be in the way. The numbers were confirmed and reconfirmed. This was it. This was the moment we had been waiting for. And by the time that certainty crystallized in our minds, critical weeks had already evaporated. During those precious early days, while scientists were still arguing about orbital mechanics and origins, Oumuamua tumbled through space, revealing its secrets to no one. Observations suggested it was roughly 800 feet long, but only about 80 feet wide, an elongated cigar shape unlike any asteroid or comet in our solar system. It spun through the void every 7 to 8 hours, its surface dark and reddish, baked by cosmic rays during its long journey through interstellar space. Some measurements suggested it was accelerating slightly, pushed by forces that shouldn't exist for a simple asteroid. Was it outgassing like a comet, even though we detected no tail? Was there another explanation for that subtle, impossible acceleration? These questions hung in the air, tantalizing and frustrating as the object continued its relentless retreat. By the time Breakthrough Listen, a major SETI initiative funded by billionaire Yuri Milner, began radio telescope observations of Oumuamua in mid-December 2017. Nearly 2 months had passed since its discovery. The Green Bank Telescope in West Virginia, one of the most sensitive radio instruments on Earth, pointed its massive dish toward the dwindling speck and listened. Scientists tuned across billions of radio channels, searching for any signal, any pattern, any deviation from random noise that might suggest artificial origin or technological activity. They listened for hours, then days, sampling frequencies from 1 to 12 gigahertz, the range where alien transmitters might broadcast. The silence they received was complete, absolute, deafening in its emptiness. No radio signals emanated from Oumuamua. No repeating patterns, no encoded messages, no carrier waves. Just the cold static of the universe, the background hiss of cosmic radiation, the electronic whisper of distant galaxies. That silence was perhaps more haunting than any signal could have been, because it told us nothing. We couldn't rule out artificial origin based on silence alone. Perhaps the object was a probe whose transmitters had died millions of years ago. Perhaps it communicated in ways we couldn't detect. Perhaps it was simply a rock, a cosmic coincidence, a fragment of an alien world kicked into the void by some long-forgotten gravitational disturbance. We would never know, because we couldn't get close enough to touch it, to analyze it, to understand what it really was. The astronomical community watched helplessly as Oumuamua crossed the orbit of Jupiter in May 2018, still accelerating, still escaping. By this time, it was far too faint for most telescopes to observe. The last images showed only a dim point of light, indistinguishable from distant stars, carrying with it all the answers we would never receive. By early 2019, it had passed beyond Saturn's orbit. By 2021, It had left the observable solar system entirely, joining the darkness between stars. In a few decades, it will become impossible to track even with our most powerful instruments. In a century, it will be light years away, continuing its journey through the galaxy, perhaps toward another star system where other beings might notice its passage and wonder about its origins, just as we did. In the aftermath of this cosmic missed opportunity, scientists began to ask the obvious question: could we have done anything differently? This question led to Project Lyra, a series of retrospective mission design studies that examined whether we could have reached Oumuamua with existing or near-term technology. The results were illuminating and deeply, tragically frustrating. Researchers at the Initiative for Interstellar Studies determined that yes, we could have reached it, if we had launched within a very narrow window immediately after discovery, using a heavy-lift rocket like the Space Launch System, or Falcon Heavy, combined with a Jupiter gravity assist, and perhaps a solar Oberth maneuver to gain additional velocity, a spacecraft could have intercepted Oumuamua within a reasonable time frame. The mission would have been expensive, risky, and technically challenging, but it was possible. We had the tools. We had the capability. What we lacked was preparation, will, and time. Alternative designs explored even more exotic possibilities. A spacecraft equipped with solar sails could have used the sun's radiation pressure to accelerate to incredible speeds, potentially catching Oumuamua within 5 to 10 years of launch. Nuclear electric propulsion systems, technology that exists on drawing boards and in prototype form, could have provided the sustained thrust needed for such a chase. Some proposals suggested launching multiple probes in succession, each one pushing the boundaries of our engineering capabilities, ensuring that at least one spacecraft would reach the target. All of these missions were theoretically achievable. All of them remained trapped in the realm of what if, rendered impossible by our lack of foresight and our bureaucratic inability to act quickly when the moment demanded action. The failure was systemic and multifaceted. Space agencies operate on long planning cycles, with missions designed years or even decades in advance. Budgets are allocated through political processes that move at glacial speed. Launch windows are scheduled around payload manifests and range availability. The idea of a rapid response interstellar mission, launched on short notice to intercept an unexpected target, simply didn't exist in anyone's operational framework. We had no designated spacecraft standing ready, no pre-allocated budget for emergency missions, no decision-making structure capable of authorizing a multi-billion-dollar launch within days or weeks. The entire system was optimized for predictability and caution, not for seizing fleeting opportunities that might never come again. Perhaps most painful is the realization that we were warned. Scientists had published papers predicting that interstellar objects might pass through our solar system occasionally, perhaps as often as once per year, though most would be too small or too fast to detect. Some researchers had even proposed the idea of standby missions, spacecraft that could be rapidly deployed to investigate such visitors. These warnings went unheeded, filed away as interesting theoretical exercises but not urgent enough to justify budget allocations or engineering resources. We knew the possibility existed, and we chose not to prepare for it. That choice haunts us now. The tragedy of Oumuamua extends beyond the scientific data we failed to collect. It represents a broader failure of human civilization to act on our stated values. We claim to prioritize exploration, discovery, and the search for our place in the cosmos. We build museums and monuments celebrating human curiosity. We tell children to reach for the stars, to dream big, to never stop asking questions. Yet, when the universe handed us an unprecedented gift, a visitor from another star system, we fumbled it through bureaucratic inertia and short-term thinking. The disconnect between our aspirations and our actions has rarely been more stark. Oumuamua is gone now, billions of miles away, and accelerating into the cosmic dark, carrying with it secrets we will never uncover. We had one chance, a singular opportunity that may not repeat itself for generations, and we missed it. Other interstellar objects will surely pass through our solar system in the future. We've already detected a second one, Comet Borisov, in 2019, but that too flew past before we could mount a mission. Another opportunity squandered, another failure to learn from our mistakes. Somewhere out there between the stars, Oumuamua continues its journey, indifferent to our regrets, oblivious to what it represented to the apes on that small blue world, who watched it pass and realized, too late, what they had lost. We thought Oumuamua was a singular mystery, a cosmic anomaly that would stand alone in our records for decades, perhaps centuries. For 2 years we convinced ourselves it was an outlier, a statistical fluke that we'd been fortunate enough to witness. Then, on the 30th of August, 2019, astronomer Gennady Borisov was scanning the night sky from his observatory in Crimea when his telescope captured something that would fundamentally change that narrative. Another visitor from beyond our solar system had arrived. The object, eventually designated 2I/Borisov, was moving through our cosmic neighborhood at over 33 kilometers per second. Its trajectory traced a hyperbolic path that left no doubt about its origin. This was the second confirmed interstellar object humanity had ever detected, and unlike its predecessor, this one behaved exactly as we expected a comet to behave. It had a visible coma, a tail streaming behind it as solar radiation sublimated its icy surface. Spectroscopic analysis revealed familiar compounds: water ice, carbon monoxide, cyanide. Everything about Borisov was reassuringly normal, textbook almost, following the rules that comets are supposed to follow. And that normality made Oumuamua's strangeness infinitely more disturbing. Think about what this comparison revealed. What? Here was proof that interstellar objects could and did enter our solar system behaving exactly as predicted by our models. Borisov's composition matched what we'd theorized for eons about comets from other star systems. Its outgassing created acceleration forces that astronomers could measure and explain. There were no mysteries, no anomalous behaviors, no need for exotic theories. It was simply a comet that happened to originate from somewhere else in the galaxy, passing through our little corner of space on its eternal journey. Which meant that Oumuamua's deviations from expected behavior couldn't be attributed to our misunderstanding of interstellar objects in general. The problem wasn't that we didn't know what to expect. The problem was that Oumuamua specifically refused to conform. Scientists immediately began running comparative analyses, and the differences were stark. Borisov outgassed in a perfectly normal way. Oumuamua showed no cometary activity whatsoever. Borisov's acceleration could be explained by standard rocket effects from sublimating ice. Oumuamua's acceleration remained unexplained, requiring either a completely invisible outgassing mechanism or something else entirely. Borisov looked like a comet, acted like a comet, and was demonstrably a comet. Oumuamua looked like nothing we'd ever seen, and acted like nothing in our experience. The discovery of Borisov forced the scientific community to confront an uncomfortable truth. The anomalous nature of Oumuamua couldn't be dismissed as the expected weirdness of interstellar visitors. We now had proof that interstellar visitors could be normal, which meant Oumuamua's abnormalities required serious explanation. But there was something even more unsettling that emerged from the discovery of these two objects within just 2 years of each other. Statistical models began painting a picture that many found deeply disturbing. If we had detected 2 interstellar objects in such a short span, given the limitations of our detection capabilities and the narrow slice of sky we actively monitor, the mathematics suggested something profound. These visitors weren't rare at all. Researchers from Harvard, the University of Hawaii, and other institutions began crunching the numbers. They factored in telescope sensitivity, observation time, the percentage of the sky under consistent surveillance, the speed at which these objects traverse our solar system, and their relative brightness. The models that emerged suggested that between 2 and 10 interstellar objects pass through the inner solar system every single year. Some models pushed that number even higher. Every year, multiple visitors from beyond our solar system, sailing through the space between Earth and Mars, most of them completely undetected. The implications of this statistical reality are staggering. For all of human history, for every year that our species has looked up at the night sky, objects from other star systems have been passing through our cosmic backyard. They've been here during the construction of the pyramids, during the fall of Rome, during both world wars. They were here before humans existed, and they'll be here long after we're gone. We just didn't have the technology to see them until 2017. And even now, with all our telescopes and detection systems, we're missing most of them. We're missing them because they move too fast, because they're too small, because they approach from angles we're not watching, because our telescopes are pointed somewhere else when they make their closest approach. We're missing them because space is incomprehensibly vast, and these objects are incomprehensibly small by cosmic standards, and our ability to monitor everything happening in our own neighborhood is embarrassingly limited. This raises a question that keeps astronomers awake at night. What were the ones we missed actually like? Were they normal objects like Borisov, or were they anomalous like Oumuamua? And if we assume a distribution, if we assume that anomalous objects comprise even a small percentage of interstellar visitors, how many strange objects from beyond our solar system have passed through without our knowledge? Then came the discovery that transformed this from a theoretical concern into something far more immediate and disturbing. In 2022, a physicist named Amir Siraj was working with Abraham Loeb at Harvard, sifting through historical data on meteors and fireballs. They were looking for objects with unusual velocity signatures, velocities that might indicate an origin beyond our solar system. What they found in the data made the Oumuamua mystery feel almost quaint by comparison. On the 8th of January, 2014, 3 years before we detected Oumuamua, 3 years before we even knew to look for interstellar objects, a meteor, approximately half a meter in diameter, had slammed into Earth's atmosphere above the Pacific Ocean near Papua New Guinea. The impact velocity was 45 kilometers per second. Analysis of its trajectory revealed an orbit that was unbound from the Sun. This wasn't a piece of solar system debris. This was an interstellar meteor, the first interstellar object known to have reached Earth. And we only discovered its significance 8 years after the fact, buried in historical sensor data. Think about the timeline. An object from another star system hit our planet in 2014. It burned up in our atmosphere, fragmenting into potentially thousands of pieces that fell into the ocean, and we had no idea. The sensors that detected it were designed to monitor for nuclear detonations, not to track interstellar visitors. The data sat in classified databases for years before it was declassified and released to researchers who knew what to look for. For 3 years after that impact, we lived in ignorance of the fact that interstellar objects could reach Earth. We didn't know they were coming. We didn't know to look for them. And one had already arrived. The meteor, now designated CNEOS 2014-08, after the Center for Near-Earth Object Studies database where its data was stored, opened up terrifying new questions. If an interstellar object hit Earth in 2014, how many others have hit before that? How many have we missed in the centuries and millennia before we had any detection systems at all? How many are in our future? Loeb and his team began planning something unprecedented. They wanted to mount an expedition to retrieve fragments of the meteor from the Pacific Ocean floor. The impact site was identified based on the trajectory data. The depth was challenging but manageable. And if they could recover fragments, if they could analyze the actual composition of an interstellar object, rather than relying on distant spectroscopy or theoretical models, the scientific value would be immeasurable. The expedition launched in June of 2023. A team of researchers aboard a vessel equipped with deep sea recovery systems traveled to the waters north of Papua New Guinea. They dragged magnetic sleds across the ocean floor, collecting samples from the predicted debris field. What they brought up included dozens of spherules, tiny molten droplets of metal that had formed as the meteor vaporized in the atmosphere. Analysis of these spherules revealed unusual compositions. Some contained isotopic ratios and elemental abundances that differed from typical solar system materials. The team reported finding levels of beryllium, lanthanum, and uranium in combinations not commonly seen in terrestrial or solar system meteorites. Whether these anomalies definitively prove an interstellar origin remains debated within the scientific community, but the implications of what they're attempting are profound regardless of the final verdict on these specific samples. Because here's what keeps researchers awake at night. If we've confirmed at least one interstellar meteor impact on Earth, and if statistical models suggest multiple interstellar objects pass through the inner solar system yearly, the mathematics becomes deeply unsettling. Over thousands of years, over millions of years. How many interstellar objects have struck our planet? How many are embedded in our geology, indistinguishable from terrestrial rock unless we know specifically what to look for? And then there's the question that lurks at the edges of these discussions, the question that most scientists are reluctant to voice, but that haunts the subtext of every paper on interstellar visitors. What if some of these objects aren't natural? What if some aren't just passing through? The statistical models that predict 2 to 10 interstellar visitors yearly are based on assumptions about random distribution, about objects ejected from other star systems during planetary formation or gravitational interactions, wandering the galaxy on eternal random walks. But randomness assumes no intention. Randomness assumes no selection. If even 1% of interstellar objects were directed rather than random, if even a tiny fraction were aimed deliberately, our detection systems wouldn't know the difference. A probe moving through our solar system would look exactly like an asteroid or comet from another star. We wouldn't know its purpose. We might not even know it was artificial unless it wanted us to know. And Oumuamua's anomalies, those troubling deviations from expected behavior that have never been satisfactorily explained, take on a different weight when viewed through this lens. The object that accelerated without visible outgassing. The object with the extreme elongated shape or perhaps the flat disk geometry. The object that tumbled in ways that suggested it wasn't a simple rock. What if it wasn't alone? What if it wasn't the first? The 2014 meteor hit Earth 3 years before we knew to look. How many others came before? How many were larger? How many survived entry and lie intact somewhere on our planet's surface, waiting? Space agencies are now developing improved detection systems, wider surveys, faster response protocols. But the gap between what we can detect and what's actually out there remains vast. We're getting better at seeing these visitors, but we're still missing most of them. We're still vulnerable to surprises from objects we didn't see coming. And somewhere in the dark between stars, more visitors are already on their way. Some are natural, debris from ancient collisions and stellar upheavals, mindless wanderers that will pass through and continue into the endless night. But if the statistics are right, if multiple objects arrive every year, the probability that all of them are natural, that none carry intention or purpose, decreases with every passing year. We're not alone in the cosmos. That much is now certain. The visitors are real, they're here, and they've always been here. The only question is whether they're all just passing through, or whether some have other reasons for coming, and whether we'll recognize the difference before it's too late. The radio telescopes turned skyward on December 11, 2017, scanning desperately for signals that should have been recorded months earlier. Breakthrough Listen, the most comprehensive search for extraterrestrial intelligence ever funded, had finally trained its instruments on Oumuamua. But by then, the object was already racing away from us at nearly 58,000 miles per hour, tumbling end over end into the darkness between stars. The scientists knew they were late. They knew they might have already missed the most important message humanity would ever receive. For 10 hours, the Robert C. Byrd Green Bank Telescope in West Virginia swept through 4 radio bands, listening for any whisper of artificial transmission. The data came back clean. Silent. Ida. Nothing but the ambient hiss of cosmic background radiation. The scientists published their findings with careful language, noting that their observations covered only a narrow range of frequencies during a limited time window. What they didn't emphasize in the abstract, what got buried in the technical specifications, was the mathematical reality. If Oumuamua had been broadcasting during the 8 weeks before anyone realized it was anomalous, we simply weren't listening. By the time we thought to ask the question, the answer was already millions of miles behind us, receding at relativistic speeds. Dr. Rachel John sits in her office at the SETI Institute in Mountain View, California, and she doesn't hide her frustration when discussing those lost weeks. She speaks about protocols, about the lag between astronomical discovery and communication with radio astronomy facilities, about the bureaucratic machinery that has to grind into motion before telescope time can be allocated. But underneath the procedural explanations, there's something else in her voice, something that sounds remarkably like grief. Because the uncomfortable truth that keeps her awake at night is this: If Oumuamua was a probe, a message, an invitation, we didn't just fail to understand it. We failed to even notice it until it had already delivered its payload and departed. Whatever it came to do, it may have already done. The mathematics of interstellar messaging presents a brutal constraint. Light and radio waves travel at the cosmic speed limit, but even at that velocity, conversations between stars would span centuries or millennia. If you wanted to communicate with another civilization, sending a physical object, a probe carrying information directly to their doorstep, might be the only practical option. This isn't science fiction. This is strategic communication theory applied to cosmic distances. And once you accept that framework, once you acknowledge that probes make more sense than broadcasts, everything about our search for extraterrestrial intelligence shifts into a more disturbing register. In 2019, researchers at the University of Edinburgh published a paper that changed the conversation entirely. They had built a computer model to answer a specific question. If an alien civilization wanted to explore the galaxy using self-replicating probes, what would be the optimal strategy? Not the fastest strategy, but the most efficient use of energy and time. Their simulation surprised them. The answer wasn't to blast probes outward in all directions at maximum speed. The answer was to wait, to use the natural movement of stars as a gravitational assist network, to send probes drifting on carefully calculated trajectories that would harness the gravity of passing stars, to slingshot from system to system over millions of years. The probes would be patient. They would be silent. They would arrive at target systems not in a blaze of obvious activity, but in a whisper of orbital mechanics. When the researchers mapped out the optimal trajectories their simulation produced, they felt something shift in the room. The paths matched known interstellar objects. The approach angles, the hyperbolic orbits, the velocity profiles. The fictional probes their computer had designed would look exactly like Oumuamua. Dr. James Corvin, an astrodynamics specialist at MIT, went further. He calculated backward from Oumuamua's trajectory, tracing its path through space like rewinding a film. The object had come from the direction of Vega, arriving at our solar system from the precise angle that would allow it to execute a perfect gravitational slingshot around our sun. If you were designing a probe to gather maximum information about our solar system while expending minimum energy, you would aim it exactly where Oumuamua came from. You would give it exactly Oumuamua's velocity. You would send it on exactly Oumuamua's path. The trajectory wasn't just consistent with artificial origin. It was textbook optimal. It was what an engineer would design if the engineer had millions of years to plan the mission and wanted to guarantee results. But the most unsettling proposal comes from a quieter corner of the astronomical community, from researchers who study what they call lurker probes. The hypothesis is simple and profoundly disturbing. If you wanted to observe a developing civilization without interfering, without revealing yourself, you wouldn't announce your presence. You wouldn't broadcast. You would send something that looked natural, something that would be mistaken for a comet or an asteroid, something that could drift through the target system, cameras and sensors recording everything, then depart before the locals developed the technology to examine it closely. You would design it to be overlooked. Think about the timing. Oumuamua arrived just as our technology reached the threshold where we could detect it, but still lacked the capability to reach it. It appeared at the exact historical moment when we would see it, but couldn't touch it. When we could ask questions, but couldn't demand answers. The window was narrow, perhaps deliberately so. A civilization monitoring our development would know when we reached this stage. They would know when we built telescopes powerful enough to spot interstellar visitors, but still decades away from intercepting them. And if you wanted to conduct surveillance on a species just waking up to its cosmic context, that's precisely when you would schedule the flyby. The lurker hypothesis suggests that Oumuamua wasn't the first. It suggests that objects like it have been drifting through our solar system for as long as our solar system has existed, each one a patient observer, each one waiting for something interesting to observe. Most would have arrived during the billions of years when Earth was lifeless or inhabited only by microbes. Those probes found nothing worth reporting and drifted on. But some might have arrived more recently. Some might have been watching when the first cities rose in Mesopotamia. Some might have been watching when the first radio signals leaked into space. Some might have been watching when we detonated the first atomic bomb and announced ourselves as a technological species capable of both vast creation and vast destruction. And one perhaps arrived in 2017 to confirm what its builders suspected. We're still here. We survived our infancy. We're worth a closer look. But here's where the timeline becomes truly chilling. Oumuamua didn't just happen to wander past our solar system. Its trajectory required planning, required calculation, required someone to point it at our sun and set it moving through interstellar space. And given its velocity and the distances involved, that launch must have occurred millions of years ago. Possibly tens of millions of years ago, when our ancestors were still small primates in African forests, when the future existence of human civilization was nothing but a possibility flickering in the evolutionary noise. Someone looked at our yellow sun from a vast distance and made a prediction. They calculated that by the time their probe arrived, something interesting would be here. Something worth observing. They couldn't have known what we would look like, what we would call ourselves, what languages we would speak, but they knew, with apparent certainty, that we would be here. That intelligence would emerge on the third planet. That this particular solar system, out of billions of candidates, was worth the investment of sending an observer. They predicted our existence before our species existed. The implications metastasize in the mind like ice crystals forming in supercooled water. How did they know? What do they understand about the development of life and intelligence that we don't? What equations did they solve? What patterns did they recognize in stellar composition or planetary formation that allowed them to look at a young solar system and say with confidence, this one will produce observers of its own, given enough time? The predictive power required staggers the imagination. It suggests an understanding of cosmology, biology, and evolutionary dynamics so far beyond our current knowledge that we might as well be insects trying to comprehend calculus. And if they could predict we would be here, what else have they predicted? Did they predict what we would do when we finally noticed their probe? Did they predict we would argue about its nature, split into factions of believers and skeptics, ultimately do nothing as it sailed away? Did they predict the exact decade, perhaps the exact year, when our technology would reach the threshold of detection? Are we following a script they wrote eons ago, performing our role in a scenario they calculated down to the smallest detail? The breakthrough listen observations, conducted too late and across too narrow a frequency range, revealed nothing. But absence of evidence is not evidence of absence, especially when the search was constrained and delayed. If Oumuamua was broadcasting, it might have done so during those first weeks when it was closest to Earth, when its signal would be strongest, when no one was listening. Or it might have been designed to transmit on frequencies we haven't thought to examine, using modulation techniques we haven't invented, encoding information in ways our current technology couldn't recognize. A truly advanced civilization would know that a developing species like ours would search in predictable ways. They would know we would look for radio signals because radio is what we use. If they wanted to remain undetected, they would simply communicate using something else. Or perhaps the probe wasn't designed to communicate with us at all. Perhaps it was only meant to observe and record, to gather data and carry it onward to the next star system, where it would rendezvous with other probes, share information, update its programming, then continue the endless survey. In that scenario, we're not the intended recipients of a message. We're the message itself. We're the data being collected, cataloged, and filed away in some vast extraterrestrial archive. Our wars and cities, our broadcasts and satellites, our hopes and fears, all of it recorded by silent instruments we mistook for a tumbling rock. Dr. B. Jiang keeps a photograph on her desk, a Hubble image of Oumuamua reduced to a single point of light against the star field. It's not a dramatic picture. There's nothing obviously alien about it. It looks like 1,000 other astronomical images, a dot among dots. But she keeps it there as a reminder of what happens when we're not paying attention. She keeps it there because somewhere in the back of her mind, in the place where scientists allow themselves to acknowledge their deepest fears, she wonders if that dot was looking back at them. She wonders if somewhere in that speck of reflected sunlight, cameras were recording her world, her civilization, her species. She wonders what the report said when it was compiled and sent onward into the dark. She wonders if we passed the test, whatever the test was. And she wonders what comes next. Because if Oumuamua was a probe, if it was sent by a civilization capable of predicting our emergence millions of years in advance, then they're still out there. They're still watching. They've accumulated 4 billion years of data about our planet, observing its evolution from a lifeless rock to a world covered in cities and industry. They've watched the entire story unfold. They know how we began. And if their predictive models are as accurate as Oumuamua's arrival suggests, they might already know how we end. The object is gone now, beyond the reach of our fastest rockets, tumbling through the space between stars at speeds we can't match. We had one chance to examine it closely, to send a mission, to get answers. We didn't. We watched it leave. And now we're left with questions that may never be answered, with possibilities that refuse to resolve into certainties. Was it artificial? Was it watching us? Did we fail some cosmic test by letting it pass unremarked and unexamined? Or worse, did we pass exactly as predicted, performing our role in a much longer game, whose rules we cannot begin to fathom? The night sky looks different now for those who know the story. Every meteor, every comet, every anomalous asteroid becomes a potential question mark. How many others have passed through our solar system unnoticed because we weren't looking? How many others are here right now, silent and patient, waiting for something we haven't yet done? And the most disturbing question, the one that transforms astronomy from an abstract science into something that feels uncomfortably like being observed. If they predicted we would be here, what else might they have predicted? Way. Right now, at this very moment, Oumuamua is beyond the orbit of Neptune, tumbling through the outer darkness of our solar system at more than 58,000 miles per hour. It passed the point of no return years ago. No spacecraft we could build, no probe we could launch, not even with every technological advancement we might achieve in the next decade, could ever catch it. The object that arrived unannounced in October of 2017, that disrupted our understanding of interstellar visitors, that forced us to confront possibilities we had relegated to science fiction, is now permanently beyond our reach. And we still don't know what it was. The scientific debate hasn't been resolved. It has only deepened, grown more complex, more fractured. The data we collected during those frantic few weeks of observation, those hurried measurements and desperate calculations as Oumuamua accelerated away from us, have been analyzed and reanalyzed countless times. Every examination yields new questions. The non-gravitational acceleration remains unexplained by conventional models. The tumbling motion, the extreme elongation, the peculiar reflectivity, the absolute absence of any cometary tail or outgassing despite behavior that suggests outgassing must be occurring. All of these observations sit uncomfortably with everything we thought we knew about objects moving through space. Astronomers have proposed increasingly exotic explanations. Hydrogen icebergs that would sublimate without visible traces. Nitrogen ice fragments from a Pluto-like world in another star system. Fractal dust aggregates held together by forces we barely understand. Each theory attempts to account for some of the anomalies while struggling with others. None fits perfectly. None explains everything. And then there are the scientists who won't let go of the artificial hypothesis, who point to the accumulation of unlikely characteristics and ask how many coincidences we're expected to accept before we consider the alternative. They've been marginalized, certainly, relegated to the fringes of acceptable academic discourse. But their questions remain unanswered. If you wanted to design a probe that could traverse interstellar space efficiently, might it not look exactly like Oumuamua? Flat, reflective, accelerating using solar radiation pressure? The James Webb Space Telescope has now shown us what's possible with light sails. We're developing the technology ourselves. The Vera Rubin Observatory is coming online soon, formerly known as the Large Synoptic Survey Telescope, a massive eye that will scan the entire visible sky every few nights. When it becomes fully operational, astronomers estimate it will detect hundreds, perhaps thousands of interstellar objects passing through our solar system. Oumuamua wasn't unique. It was simply the first one we noticed. There are others out there, have always been others, drifting through the space between stars, occasionally falling through our tiny corner of the galaxy. We just never had the instruments sensitive enough to see them. What happens when we find the next one? And the one after that? Will they all be equally strange, equally inexplicable? Or was Oumuamua truly an outlier, something different from the cosmic debris we'll begin cataloging? The uncomfortable truth is that we're about to be confronted with these questions again and again, forced to reckon with objects we cannot study adequately, visitors that appear and vanish before we can mount proper investigations. We're building the detection systems, but we're not building the response capability. We still can't chase them. We can only watch them leave. Oumuamua is still out there right now, still tumbling through the cosmic void, moving farther from our sun with every passing second. If it's just a rock, an irregular fragment of some long-destroyed world, then its story is simple cosmic happenstance. But if it isn't, if somewhere inside that strange tumbling form there are instruments still functioning, still recording, still observing, then it's carrying data now. Data about us, about Earth, about the civilization it encountered, however briefly, in this remote spiral arm of the Milky Way. Think about what it would have seen. Our satellites in orbit, our radio transmissions bleeding into space, our cities lit up on the night side of the planet. If it was designed to gather information, it succeeded. And that information is leaving with it, encoded in whatever medium an alien technology might use, traveling outward into the galaxy at nearly 60,000 miles per hour. Somewhere out there, perhaps centuries from now, perhaps millennia, that data might arrive. Something might be waiting to receive it. Something might process the information Oumuamua collected, analyze what we are, what we've built, what we're capable of, and then that something might decide what to do next. We have no way of knowing. We have no way of stopping it. The object is gone, beyond recall, beyond reach, carrying its secrets into the darkness between stars. Every question we have about Oumuamua will remain a question. The mystery doesn't resolve. It simply recedes, growing more distant with each passing year, until eventually it becomes just another unsettling footnote in the history of astronomy. The visitor we couldn't explain. But it's still there, still moving, still tumbling through space on a trajectory that will carry it past other stars, other worlds, other possibilities we can barely imagine. And if something is watching from those distant places, if something is waiting for the data to arrive, then they're learning about us right now, in this moment, as we go about our lives unaware that we've already been observed, already been cataloged, already been assessed by intelligences we cannot comprehend using criteria we cannot guess. The cosmos is watching, and we cannot look away from what that might mean. That's where this journey ends for tonight. If you made it all the way here, subscribe and hit the bell for more long-form stories like this. Check out the videos on screen for more right now. Drop your own experiences in the comments below. Thanks for listening, and I'll see you in the next one.